So, hello everyone. Thank you for joining in. Thank you, Ziad sir. Thank you, Narayan. Thank you, Anita ma'am. Thank you, Ritesh. Thank you, Vinit sir. Yes, so I can see Vinit sir, you say doing module one still. So I think that is perfectly fine. If at all you feel that you can do both of these parallelly, also that is completely fine. Right. I hope if you have any queries in module one also, you can definitely ask us out. Right. That is great. Okay. So let me share my screen. So the people who have recently joined, point you out in the right direction. I request people to. Okay. So let me share my screen. I hope my screen is visible now. Great. Okay. So yesterday we covered the simple linear regression. Just maybe 2 code runs we have not. We will cover that and then move into our next lecture. So for the people who have recently joined the community, right? So how many of you have recently joined, like in the past month? If you've joined in the past month, type me in the chat box. People who are joining us. Yeah, thank you so much, Anita ma'am. Great. For people who are joining us on our social channels, you can use the comment section or the chat section. Recently joined, Narayan sir. So basically, the whole point of Vinit sir, exactly 12 days back. Thank you so much, Ziad sir. So I'll point you out how to go forward because we have many people who have recently joined. So we have people who are joining us on our YouTube live link also. So I'm going to address all of them. So if at all you have recently joined, you can begin from the module 1 here, right? So which will be Python basics. If you are familiar with Python basics, you can kind of fast forward or move into the next sessions, right? So these are the primary lectures. These are covered by the primary faculty, either by Jain sir or Rajiv sir, right? So you can see that these are all covered from module 1, and we keep continuing, module 2, module 3 and all. So what do we do in revision hackathons is we are going to revise each of the lecture that was taught by the primary faculty. Here, either Jain sir or Rajiv sir. So in that fashion, we have completed the revision hackathon for the module 1.1, 1.2, 1.3, and so we have continued like that. We've not covered the sprints yet, right? So because sprint is more of an exercise to you, so you can go through the lecture and directly attempt the sprint, right? So, and now very recently we completed the module 2 revision, and then we are now in the module 3. So the question might be, so because you are in the beginning, how do I catch up, or how is that I can understand the revision hackathon? You need not. So the revision hackathons happen in a cyclic manner, right? So once we finish all of the modules, we are going to begin, another faculty or someone is going to begin from the start, right? So there are 2 ways to either catch up. If you plan on doing that, you can go through the primary faculty's lecture from module 1 and also join the current session like Vinit sir you are doing, or you can do is watch the primary faculty as lecture and continue in that particular fashion only. And the recordings of the revision hackathons will be there in your inner circle, right? So this particular lecture is the course on your Teachable is called IT Madras CC and Pixeltest AI, and you'll also have inner circle. In that inner circle, you can see that there will be all of the sessions, the previous hackathon, revision hackathon sessions also, right? So you can, what you can do is you can finish 1.2, the primary lecture, you can start here and then go to your inner circle and see the revision hackathon. So there's nothing much actually you're missing. And when you're going through from the beginning, if you miss any point, like if you come across a speed breaker or a roadblock, if you have any query, you can bring them to the the revision hackathon session, right? So towards the end, we're going to take questions. It can be related to the current lecture or any of the previous lectures, right? So I hope this is clear. If this is clear, type C in the chat box. Yeah, so Ziad sir asks, during which days in week AI hackathons? Thank you, Vinitha. Thank you, Anita ma'am. Which session starter should not miss, right? So Ziad sir, if you see the email reads, the email also says we do sessions on Wednesday, Fridays and Saturdays for AI, right? Thank you so much, Ravindra sir. Right?
Hi, good evening, Pramod this side.
Yeah,
Basically, yesterday due to basically I was not means available. So in fact, you
today,
called me. So today we'll connect after this meeting.
yeah, I tried calling you, but
Yes,
you
yes,
said
yes,
we'll catch up later. No worries, sir.
yes.
We'll do it.
Okay. Yeah, please.
Okay, so let's begin. So we are now in this session 3.2. We finished 3.1 yesterday. We are in 3.2. Okay, so in 3.1, we just wanted to cover a few points, right? So yesterday, I'm just giving you a quick recap. So yesterday, what we have done, we wanted to know the correlation, right? So when you're talking about linear regression, we are talking about correlation. Are any of the two elements related or not? So we were working with a data set which was strangely called long bones, where there are a few bone samples which had a different nitrogen composition and their intermittent time, like the time, how long they have been underground, right? So all of that time, so we were trying to work with nitro, age and time. So primarily two variables. We were looking at nitro column and time. So what we did, we first cleaned the data of the null values, right? So people who are joining recently, do not be overwhelmed. You will be handheld from, if you go through the sessions, everything becomes clear, right? So I would request you to go through it, just try to overview, understand, right? So you need not have to deeply go through it. You can definitely go through the recording, right? So we plotted the nitro composition and the time on the graph. And how did we do that? People who have joined recently, there are a few functions which we use to do the plotting, right? So there's nothing heavily you have to do. I'd guide you. If you have face any challenge, you can always reach out, right? So that's not a problem, right? Then we have understood that there is some relation, and we named that relation also. Here in this case, it was a negative correlation, and we also understood what is a strong correlation, what is a weak correlation, right? So we've understood all of that. And then as we proceeded further, we also gave a value to our correlation, which was the correlation coefficient, which was the R value. Here for this also, you did not have to do any math by self. You could just use this function called Pearson R, and you are getting your correlation coefficient, right? So we've understood all this, and we've understood a few types of graphs, right? So there is some linear correlation and some places where there is no linear correlation. I mean, this X and Y are not correlated or related, right? So there's no common relation we could see. So we've also understood that. And we've also seen perfect correlation and like still near perfect correlation, right? So they're not perfect, but still you are able to see that there is some relation between the X and Y. So this is how we have understood yesterday. And then we have understood that, right, whenever you plot something, okay, and there is an estimated line that the OLS function that we used yesterday creates, right? So this is more of a revision. Yeah, so I think Vinit sir, you already have the contact. You can always reach out. Great. So now I've shared that on chat, personal. now you can see that, these points are scattered, but not exactly on the line. So what the model, the OLS does here is, it is going to make a prediction that, and make, plot a few points and make the line, right? Okay, so how do we do that? So we can always go ahead and do that. So this was explained here. So for example, these are your scattered points, and to get the estimated line. Yes, sir. So Naidu sir, here is. Yeah. So now this particular line, what it did is, the actual points are green points, but it estimated these red points and plotted a line via that, right? So now the difference between the actual and the estimated point is called the residual, right? So we have understood till here yesterday, right? So now we've understood the model, the OLS function. Yeah, so people who have just recently joined, you can even choose to continue or start from the beginning. So it should not be a problem, right? So you're not missing anything. And if you feel that it is something that is not, you are not able to relate to it immediately, you can definitely go forward. At the same time, I would request you to go through the module 1.1 or the module 1.2, right? So we'll soon catch up again, and then there'll be a revision hackathon happening soon. Okay? So that should not be a problem. Great. So now, yesterday we've understood. We passed into the OLS, the relation, right? The equation, which was y tilde x, right? So this was the way how we created the equation. And then we created model, and it gave us two outputs, right? So the first parameter and the 0th parameter and the first parameter. So then from that, we were able to generate the equation, which is the linear regression, the lines equation. So now you can see that minus 69.24x plus 316.8, right? So y is equal to, mx plus c kind of a line we have got, right? So this is what we understood till yesterday. And now to also understand what is the predict and the actual response, it is very easy. So for example, you have a scattered plot here, but someone wants to predict what could be the value for, say, any point on X, some different nitrogen composition. So let's say here it was X equal to 3.65, right? So now coming from the equation Y equal to, 316.8 minus 69.24x, X is given, right? So it is very easy. You're going to substitute it. So the slope is there in the variable slope. The intercept is there in the variable intercept. So basically you're just predicting by substituting X, right? So then you got a point. So for X 3.65, your prediction, the prediction is 64.06. So for 3.65, the prediction is 64 point, what was that? 06. So this is how you got the prediction. But now how do you calculate the residual? Then when you want to calculate the residual, they'll give you the actual. They'll say the observed value is 71.8. Observed is nothing but the actual, right? And then they say X equal to 3.88. For example, now you want to calculate for 3.88 somewhere here, and then you are trying to substitute within the formula. Similar fashion, you're going to say X equal to 3.88, and the slope is in the slope variable, intercept in the intercept variable. Then you got a the predicted value. Now what do? You have an observed. So residual is nothing but observed minus predicted, right? So you get the residual, right? So now you can see that here we have printed that for a skeleton with 3.88 units of nitrogen, x equal to 3.88, we predict that the body to be, the prediction came out to be 48.14, right? So I'm just giving to 38.88. The prediction came roughly to 48.14, but the actual age of the body was 71.8 years, right? So because it is not the perfect correlation, right? It could have been higher for that particular sample. So now what is the residual? Now, if you see, the residual is the difference between actual minus observed. Now we are going to do that. We're just going to subtract all of that, observed minus predicted, and then you're going to get your residual. And the residual is 23.65 years. So people who missed yesterday's lecture, and because we did a small recap, you might feel that it is you're kind of parachuting into it. Do not worry. If now we're going into the 3.2, which is today's revision hackathon. But people
one thing on daily basis, how we get the link, the recording link.
Okay, so what you're asking is, whenever the session Wednesday, Friday, and Saturday is happening, how do you get the link to join the session?
No, not link to join. Basically a recap. Basically, maybe see whatever you have you have discussed, so that we understood. But anything need to recap. So later also we can go through the recording.
Understood. So basically, what do you do is you go through the lecture. For example, right now we are in 3.1. Like we were discussing the file of 3.1, and you can see that there is this link which says the download simple linear regression.ipynb. So when you click that, this particular file will open, and when you click open with Google Colab, so you will have access to the same file, right? So
it is the existing. It is the existing. No, basically I'm talking about you. Okay, whatever you are saying, basically that we understood line by line. So if that things need to be recapped, maybe the later, maybe tomorrow, day after, or some. So we can follow that exercise accordingly.
Yeah. So you can go ahead and follow the same exercise. The same file will become your notes also, because it is planned in that way. The notes is written and the exercise also is there.
Okay.
Yeah. So you can go through that from here itself or from your Teachable. I think I've answered your question, sir. So is that clear, or you're talking about the session link or the practice link?
I'm talking about the session link.
Yeah. So basically the Zoom session link.
Yeah.
Yeah. So now when you joined today's session, sir, so you joined it, I guess, from the email.
Yes, correct.
Yeah. So basically all of the communication comes over email, and the link will always remain the same. So Wednesday, Fridays, and Saturdays, the link is going to be the same. So you will receive the email, and if at all, let's just say I'm just going to show you. There will be a YouTube live link also just below the Zoom, right? So just in case, if you go through your email, if you're not able to join the Zoom session, you can click on the image that will be below. There'll be a play icon. When you click on it, you will be able to see that live if the session is happening that time, or you'll be able to see the recorded session on the same link. Yeah. Soon after that, you will see the recording also in the inner circle.
Okay, we'll try if I get.
Yeah, so I think you'll need the access. You'll need to figure out how to access Teachable. So I'll help you with that. Not a worry.
Okay.
Right?
Okay.
Thanks for the query.
Okay. Yeah.
Okay. So so the people who have joined yesterday and understood what we have done today, the residual and the predicted and observed, if you have understood that, type U in the chat box. Thank you, Vinit. Thank you, Ritesh. Right. So now what we are going to do is we are going to our 3.2, okay, the inference for regression. I am going to share. So how do you find the link for collab? Yeah, thank you, Rajesh, sir. You can find it from here, or I can just go ahead and share this link with you. I'm going to say share. right? I've just shared the same on chat. So when you open this link, what will happen is, you'll have to go into the file and say, save a copy in Drive, right? So it will save in your Drive and you can directly open it in your new tab and make your edits and runs there. Okay. So let's proceed. Now, today's session, Inference for Regression. So I'm starting from the beginning. So we'll go through the objectives as we proceed forward. So now what we're trying to understand here is, whatever hypothesis, we have previous sessions, we have understood, the t-test or the chi-square test, we understood all of that. In our, the recent lecture, we've understood the OLS and the correlation coefficient, right? So we have understood all these. Now we'll try to kind of do all of that together, also learning the new inference ways, like when you will be able to generate new insights also, right? So now what we are going to do here is, first we'll identify the appropriate hypothesis to test for a statistically significant relationship between two quantitative variables. So basically what we are going to do is, we are going to use the same data set, which was long bones, right? So I'm going to go to view, clear all outputs. So now what I'm going to do here is, I'm going to import the same data set, long bones, into the data frame df, right? So here itself, we have dropped the null values. Wherever the null values were there, we are dropping it immediately and we are going to print it, right? So this is the data set. Okay. Now, what we are going to do here is, if you see the shape, actually there were 42 observations. When you clear the null, it will be 35 observations. Okay. Now, yesterday we have done the OLS method. Now, yesterday we had the explanation also. Now we are directly doing the OLS here. The equation is time column tilde nitro y tilde x, and we are going to get the parameters, which is the intercept and the slope in the variables parameter 0 and parameter 1. So I'm going to run it, show it to you, right? So now you see, you got the intercept, you got the slope also, and the OLS model ran, and the whole of the details of the OLS got saved in the variable model, right? So we are going to use this variable model further today to understand more insights about this model that we have run. Okay, so till here it is more of what we have done yesterday. Now today what we are going to understand is, so y is equal to mx plus c. There are different ways to represent the same. So if at all you're talking about a larger population, the y equal to mx plus c, we use b naught, or the Greek alphabet, b or ba here. So it is the same equation, y equal to mx plus c. But when you're talking about a sample model, the sample, like if you're taking just 5 observations from the whole data set, then it is a sample. And for in that case, we are going to use the equation, the small b naught plus b1x. But if we are doing the sample of the whole 35 observations, then it is capital B naught plus B1x, right? So this is what we are setting up the nomenclature. So if you have understood the nomenclature, it is the same y equal to mx plus c, but the smaller case b means it is the sample. The larger case b means it is the whole population. So if you have understood this, type U in the chat box. Thank you, Anita. Okay, so people who have recently joined, don't be overwhelmed. Try to overview, understand like the possibilities of the functions. While you cover from the beginning, it will become more and more clearer. Thank you, Ritesh. Thank you, Anita. Now, so we have clarified the nomenclature. Now what we're doing is, we'll do the t-test, right? If you remember, when you have 2 parameters or 2 columns, you can do a t-test to actually accept a null hypothesis or reject, right? So either you reject or fail to reject the hypothesis. Now we are also going to do that. Now we're not going to do it in the same fashion that we done previously. We will use a newer function, which will be a bigger, and more summarized manner, right? So first, what I'm going to do here is I'm going to run that, and then I'll come to the explanation of it, right? So now if you see the same thing, OL model has the OLS model run of time and nitro on the dataset long bones, right? So this is already run. Now you're going to do model.summary, right? So this is something that we have not done yesterday. Now we are going to do model.summary. When you do this, whatever model has run, a summary of the OLS regression results are listed out, right? So this is more of a diagnostic report. You will not have to understand all of it, right? So you'll need to only see a few things, like when you say the platelets is this much, right? You are not concerned about all of it, right? So now if you see in this model.summary, what is happening is you can see there are this particular column, this particular section. In that there is nitro, which is nothing but the slope, minus 69, which was slope, and the intercept. Okay, the intercept is 316. So we will be more focused on the slope always. So when we are trying to get any insight, we are more focused on the slope. I'll also explain why. So now I'm going to open a sheet. Now, if you see y equal to mx plus c, or here it could be y equal to b1x plus b naught. Okay, I'm just giving example. So whatever the names or variables could be, you can see that the y is majorly changing because of the slope than the intercept, right? So y is very much dependent on the x, right? So we are more, I mean this particular portion where slope is concerned, right? So slope varies, y varies, right? So the same x, and for the same y, if the slope keeps changing, the y significantly changes. So for that reason, okay, so where are we? For that reason, we are going to look at this particular values of the slope rather than the intercept. Okay, so now there are some headings, which is coefficient. Yesterday we have seen that the coefficient for the intercept and the nitro is so and so. The standard error, right? So in our previous sessions, people who have recently joined, we calculated standard errors in various ways. So there's a formula, and there is also a Python function. So you do not have to do anything manually. There's a Python formula, Python function, where you can calculate the whole column, like for example, times standard error and the nitros standard error. So that is also included in the summary, right? So this is included. So you know that this is the standard error for both of these columns, right? And then if you remember the t and the p values, right? So if you remember, we got the p value based upon the value of p. We compared it with the significance, right? So if p, so let me just show that p value in null hypothesis. So if you remember, how do you when do you reject or accept? So now whenever p value is less than 0.05, then we used to reject the null hypothesis. So correct me if there's anything. So what does p value over 0.5 mean? So a p value less than 0.5 is statistically significant, while the value of 0.5 indicates the null hypothesis is true, right? If p value is less than 0.5, we reject, like the null hypothesis becomes, yeah. So Ritesh, you have to complete it. So when p value is less than 0.5, what happens? So when p value less than 0.5 means what? This should be the question, right? So no, it's 0.05. 0.05. Correct. So 5%, it is 5%. So the test hypothesis is false and should be rejected. So this is what we have understood in our previous sessions. Now, if it is less than 5%, which is less than 0.05, we reject the null hypothesis. So now here it says P is less than 0.05 because it is 0 directly, right? So this is what it is telling. So whatever hypothesis we consider here, if you remember Ritesh and others, what normally our null hypothesis is, there is no correlation between the two parameters that we are comparing, right? So if you look at our nitro and time, what would the null hypothesis be? The null hypothesis would be that they are not correlated, right? So the alternative hypothesis would be the opposite of the correlation, right? Or the opposite of not being related, right? So because here the p-value is 0 and less than 0.05, we reject the null hypothesis, right? So how many of you have understood what we have done here, right? So because the p-value is less than 0, we have rejected the null hypothesis. And what was the null hypothesis? The hypothesis, normally the initial hypothesis is there is no correlation between nitro and time, right? But because we reject it, means that there is some correlation between X and Y, right? So if you understood this, type U in the chat box. Thank you, Vinit sir. Thank you, Ritesh. Thank you, Ravindra sir. So this is what we have done here. Now you can see that this model.summary is very useful for you to see all of this in one single summary, right? So now if there was a p-value and if it was greater than 0.05, you would see that there is some value here, and then you would go, do an inference based upon that, right? So now what is the 0.025 and 0.0975, right? So in our previous sessions, we have seen that there is the confidence interval, right? So I'm going to just show the confidence interval. Now we see that whenever the confidence interval, the regular confidence interval is, it should be between, we should be able to tell the value, whatever the slope we are trying to find out, will be between the lower limit and the upper limit, right? So the lower limit is starting from 0.025 and the upper limit is 100 minus 2.5, right? So I'm just going to show it here. So now it is showing you the lower limit 0.025 and the 0.975. What it is telling is the slope value with 95% confidence, right? So is always between, with 95% confidence, between minus 96 to minus 94. So now if I come here to our diagram, so okay, where is our, so let me plot it. Did we not plot it here? Okay, so I'm just going to show it here. Now if you see the slope, yeah, so it will be what I'm going to do here is Ci equal to none, right? Now this is Ci means confidence. Okay, so I'm just going to see if I remove the Ci, which should be, yeah. So now what is happening here is this slope will be between this line and this line. So the confidence interval states that for 0.025, it could be minus 96 and the minus 42. So these two slopes it is giving. So most of the times, the 95% of the chance is that the slope will be from here till here. So like here till here. So, and this is the actual slope that we have got. But if you want to have a confidence interval, right? What is the minimum, the lower confidence interval and the upper confidence interval that is being given in values in the same model summary, right? So the people who have recently joined, we have calculated the lower confidence interval, the higher confidence interval, the p-value, the t-value, standard error, all of these in model.summary to get all of it in a single screen, right? So if you understood this, right, and you see that the value of it, like it is simply giving all of it at once. If you understood that, type U in the chat box. Yeah, so Ritesh says, so here the confidence is 95% or 97%. It is 95. So now if you see the 95, the 0.25 before and 0.25 after, right? So if you, I think I'll clarify your doubt. So 95% of the chances your slope will be between lower limit and upper limit. And you can see that you're going to minus the first 0.25 and towards the end 0.25. So this together is 5%. So the 95% chance is that it will be in between. So do not be confused by the number which says 0.975. So it is starting from 0.025 to 0.975. So 2.5 is left out here, 2.5 is left out here. Right, so the 5% is left out and the 95% chance is it will be between here and here. 100% chance that it will be between the minimum and the maximum value, right? 95% chance it will be between -96 to -42. Okay. So I think this is what we have covered here. Now, if you go through this particular diagram here, we'll see the slope parameter. Yesterday also we have seen if the points, the scatter plot, when you do that, if they are closer, then there is a stronger correlation, right? So let me, so here the null hypothesis was there is no correlation between the two. The alternative hypothesis, there is a correlation between them. Because yesterday's session, we understood that there is a correlation and that is a negative correlation. Today, the hypothesis proved that. Yeah, so Ritesh, we have, there are parameters that you can include like, CI and all to change that, right? So most of the times we use 95%. Yeah, so you can look at the function definition and you'll be able to do that. Yeah. So, so now the question here was, is long bone nitrogen composition statistically significant, significantly associated with intermittent time? And we have understood from this summary that it is associated, right? So how did we do that? Based upon the p-value, because p-value is less than 0.05. We rejected the initial hypothesis, which was they were not correlated, right? So now we know that they are correlated. Okay, so people who have recently joined, we have covered about this in our previous session in detail, right? So should not be a problem. Right? So this is what we have done, and this model.summary comes very much handy as we proceed forward. A few more examples and it will become clearer. So today's session is more about inference from regression, right? So whatever points we are doing, you're inferring or generating insights out of that, right? So we are doing that. Now, so what we are doing here is next objective. We are going to make the connection between t-test for a population mean and a t-test for the slope coefficient. Right? So, so people who have recently joined, there is a definition or a formula for t, and there is also a way to calculate t. This was covered in which lecture? This was covered in our chi-square t-test. So we have covered it here, right? So here, right, t-test lecture 2.1, right? So we have covered it here. The formula is also there. There's also a function. So here, what we are doing here is first t equal to the x bar. So now x is the sample mean. So people who have attended, people who did not attend, do not worry. So there's this formula. So there's a sample mean. This could also be calculated, and there is the mean under the null hypothesis by standard error, right? So all of this put in t, the value minus 5.192 came. This is how you manually do it. But when you use the model summary, you directly got it, right? So this is the expanded view, and this is the summary, right? Yes. So mu naught is nothing but the mean of the population. Yeah, so it's been always that. Okay, so we you can revise the 2.1 also to be more clear and congruent with what we have done. So this is an explanation of what we have inferred right now. P less than 0.05, then we thus reject the null hypothesis and accept the alternative hypothesis, right? So now, does that mean the slope of the model for the relationship between nitrogen and time in the population is exactly equal to 60 minus 69.24, right? So as we've learned, when we are creating confidence intervals for population, the answer is probably not. So it is between the confidence interval, right? So the lower and the upper point. So this is how this has been explained, and you can see that the confidence intervals now it will be between minus 96 to minus 94 is what is being specified. So it is more of what we have discussed based upon the summary. So we have gone ahead and also discussed this, right? So if it is clear till now, like what inference we have done from the summary, type C in the chat box. Thanks, Ritesh. Thanks, Anit sir. Thanks, Ravida sir. Okay. So now what happens, right? So in what cases your summary inference might be wrong, right? So we know now, till now, this could also conclude our today's session, because we've understood how to infer based upon the model summary. But we should also know when there is a violation for the assumption, right? So we'll go ahead and do that. So we'll understand by example. So here what we are doing is we are taking a data set which is called plants.csv. People who are joining recently can see that we have a CSV file here. If you open it, you will be able to see that it is more of like an Excel data set. And we are going to import all of this into our Python model, right? So in the data frame. So the data frame's name is plants, and I'm going to print it. So the same data set shows up here, right? So you can see that the name of the island. So basically that, the area. So these are the columns in that, right? So we're not going to go in detail about all columns, but we are going to try to compare, do the inference for any of the two parameters. So in this particular data set, we are going to first look at area and species here. Okay. So now if you want to know a little bit more about the data set, so it is also mentioned here. So this particular data set, if you've done the assignment, this data set was more in detailed explained in our data set also. So we wish to use linear regression to determine if islands with a larger area are home to a greater number of species of plant. So this is what we are trying to do here. Okay. So what we are trying to do, we wish to use linear regression to determine if islands with larger area. So you can see that area and the number of species in that particular island. So we are trying to see if they are correlated, and if they are correlated, how are they related? And so we're going to see that. Now, first, what we are going to do, we are going to do a REG plot here. I'm going to run. So now when you do a plot of the same, right? So what is happening? It is giving you a plot of scatter of all the points, which says when the area was, say, lesser, the species was ranging from 0 to 100, and it is going to 600. And there are only a few points, like let's say the area was higher, let's say over 1000, but the species there were only 400. So by looking at the diagram, do you think there is a strong, or if there's any specific correlation between the area and species? Right? Okay, Ritesh. So basically now I'll try to explain. Now, if you look at our scatter plots previously, right? So let's say this particular scatter plot, even the diagrams also we see. So we could see that there's a negative correlation. But here, what is happening is most of the points are not aligned around the line, right? So basically, if because the model is going to generate an estimated line, it is given a line. But if you see this, the points are not properly distributed. Okay, yeah. So Ritesh, I think you have made an inference, and we'll see more about it, right? So this says looks like more area, more diversity in species. But is it like true congruence? Like you can see that most of the data is clustered towards lesser area islands, right? So which might mean that even in lesser areas also the number of species is higher, lower, and we are not able to surely figure out if there is a relation or not. So in our previous examples, like the long bones, nitrogen and all, you're able to see that if there will be a line that will go and most of the points will be above or below it. But here, the points, most of the points are not above or below it, right? So can you see that? So if you're able to see that, so we are not sure if there is a correlation, and which looks like there is not, we are not able to surely tell that there is a correlation. So now let's go ahead and do the mathematical operation. So when you have a scatter plot like this, how to proceed forward is something that we are looking at. Now we'll do the model summary. And how do we do the model summary? We do the OLS function over species and area. So species here, why we choose species? Because it is y tilde area, right? So we are going to do species over area, and we use dot fit function, and then we are going to print the summary. So I'm going to print it, and this will also give us a p-value. So now if we have to make a hypothesis, the null hypothesis, right? So can anyone give me what could be the null hypothesis? Right, so in the chat, can you tell me what might be the null hypothesis here? So Ritesh says there is a correlation between, but the null hypothesis is always no correlation, right? So the null hypothesis, whatever you stated is the, yeah, so Anita Devi, you're right. So there's no correlation between area and species. So whenever we talk about null hypothesis, we start by the default assumption, that is, there's not correlated, right? Thank you so much, sir. So they are not correlated. So that is the null hypothesis. But now we are going to see here, P is this less than 0.05? So we can see that, like, it is definitely yes. So which means, what are we going to assume here? So what are we going to reject the hypothesis, or are we going to, what are we going to do? Yeah, I think so Ritesh, so what we do, yeah, so you answered and you also asked a question. Okay, so Ritesh, so negative statement means negative statement is which is always so there is a difference between negative and non-positive, right? So what we do here is we say that whatever the null hypothesis, whenever we are trying to assume null hypothesis, we say the default assumption is that there is no correlation, because we have given an example in our previous sessions also. Like for example, there was one medical drug that was there, which was already helping cure one particular condition, and there was another medical drug that was created, which, as we know, the research assumes that it is better than the previous drug, but we do not start with the hypothesis that it is better than the previous drug, because until there is data to prove that it is better, we'll always assume that it is not, right? So another example. So basically, there is a court case happening, and we consider a person to be guilty or not. So until there is evidence, the person is considered not guilty, right? So that is how you start your null hypothesis. The judges and everyone's null hypothesis is he is innocent until proven guilty. That is how the null hypothesis is created, right? So negative statement can mean many things, but here we are doing the default assumption is that it is not going to be true. Now, if you see in the court case, right, what would be the negative statement be, right? So he's guilty, but what do we do here is, until we have evidence, we assume that it is not true. So that is what I mean by it doesn't have to be negative, right? So the null hypothesis starts with the assumption that we don't fall into the risk that the person gets first. If we start with the assumption that he is guilty, it will all be reversed, right? So that is what I meant. Okay, there's a lot of questions from Ritesh. Okay, so first, is the null hypothesis framing clear, Ritesh, now? Right, so you start with the, okay, so what I would request, so is anybody else has a confusion for the framing of null hypothesis? So if you're clear with framing of null hypothesis, others, you can type C in the chat box. Yes, right. So now I think I understand from where your confusion is coming, Ritesh. You are trying to do in t-test and the A/B test, right? So the null hypothesis in t-test is starts with the the non-positive statement, where, and the A/B test is different, because in t-test we are doing single variable testing, right? In A/B test we are comparing both. So when you're comparing, we say there is no relation, right? So that is where we say there is no relation, and that becomes our null hypothesis. In t-test, the null hypothesis is, in our drug case example or the guilty not guilty example, we assume that it is not, right? So not a certain value or not true, right? So I think you've got both of the definitions clear. Like you have understood t-test definition of null hypothesis clear, but you've got the A/B test null hypothesis definition clear, but you're getting confused between them. So both are for different cases. Correct. So we're going that. We're also doing here. So what we are doing here is the null hypothesis, as stated by Ravindra sir and Anita ma'am also correctly, we'll assume that the area, because we do not have evidence yet, right? So we are going to assume that the area of the island has no relation with species. So now if you're able to prove with evidence that there is, then so how the evidence comes with the p-value. Then you can say no, the null hypothesis was, then you can say we reject the null hypothesis, or we accept the, we fail to reject the null hypothesis. Okay, so I think you got both of them clear. Mostly it must be the nomenclature that is confusing, or two different cases that you're trying to comprehend at once. So I request you to once write the definitions down clearly, and it'll be clear. Right. So we'll look at all the null hypotheses further. Right. Thank you so much, Ritesh. Yeah. So now here also we've understood that the p-value is 0.01, which is less than 0.005. So which is less than 5%. So what are we going to do here? P is less than p-value. Less than means the test hypothesis is false and should be rejected, which means we accept the other hypothesis, which is that they are correlated, right? So are we on the same plane here? So if you understood, if all of you have understood that what we are doing with the null hypothesis here, type U in the chat box. Yes, thank you so much, everyone. Right, and Raja sir has put out a statement which might be helpful for you, Ritesh. It says the null hypothesis is basically to examine and verify the basic difference, if any. Right, so there are multiple ways to come at the same point. Okay, so now, but the diagram did not actually state that. Now we can see that there is some correlation, but the diagram, if you see the scatter plot, you're not able to actually do that. So that is where the violations or assumptions of linear regression can happen. So basically you might see this and think that they are not correlated, but when you look at the model summary, you can know that there is some correlation. So now what went wrong? So why are we not able to understand it directly from the diagram? So now this is where even Jain sir explains in the primary lecture that whenever you are analyzing a data, you would always be working with a subject matter expert, right? For example, we know very little about the plant observation, or the excavations of long bone nitrogen, or let's just say the temperatures of body, that kind of example that we have taken. But for, some examples are easy, like temperatures body example was a little easier. You do not need a subject matter expert because you have a little assessment of that and you can make a an understanding. But in many cases you might actually have to, like here, if you are work with a plants expert, if you are trying to do a COVID analysis, COVID related, you might have to sit with a person who is into the virologist, right? So that is where the equation or the understanding, you will have a better understanding of the same, right? So let me go ahead and see, because we are not able to get the scatter plot around the line, we might tend to assume or get confused that is there a relation between area and spaces, but the summary says that there is some relation. So what do we do then? So what do we do here is, if you consult a subject matter expert, they might say based upon an equation, right, that you might not see the relation. If you're directly comparing x with y, you might have to compare x with x square, or y square. So here Jain sir also gives an example, right? So there is the example of I'm just going to I don't recollect, so I'm just saying s equal to ut plus half at square. So now I'm just going to take an example some of you might be relating to. So now there is this one relation where we are trying to talk about distance, and is distance related to time, right? So now do not we're not going into the detail of this, right? So this is an equation you might have come across in your college days or school days, right? Now distance ut, here u velocity, time, and then half at square. So now let's assume the initial what Jain sir says is, if let's say initially the body might be in rest, then s equal to half at square, And you might think that if you are trying to compare S with T, you might not get a direct correlation, but S is, correlated. Okay, I'm just going to related to not T directly, but it is T square, right? T to the power. It's always, T to the power. Yeah, here. Okay. Okay, I'm not able to, T to the power 2, right? So when you talk to a subject matter expert, they'll give you that the equation that you're trying to directly correlate, S and T, you'll not be able to get a strong correlation or a clear correlation. But if you try to map S with T square, you'll get a better assessment, right? So this is what happens. So now in here, when you sit with a subject matter expert who is into, let's say, observation of plants or in the science of plants, what happens is they might tell you that try to plot area not with direct, so just give me a second, directly with species, try to plot it with the log of the area, right? So I'm just going to do that. So you do not have to know how. Okay, so these are not basically these are just the graph plots, so you can ignore this. So what we are doing here is I'm going to just remove this dist plot. I'm going to run it. Now what we have done here is we have created the column called log area, which is added, which is the formula np.log of the column. So basically wherever the area was there, the log of the logarithmic, log of that particular value got added into that particular data frame, right? So this is the, syntax for adding a column, right? Right. So now we have added the column called log area, and this formula works like this, right? So log E, I'm going to say it here, like for example, equal to, I'm just going to say log E. This also sir explains in the session. So I'm going to say log E calculator. Okay, I'm going to open this. Now, you do not have to actually do this. So basically, I'm just going to give you an example. So this is 0.8. And I'm going to say 0.8 and see if it is matching. This is minus 0.2, right? So all of the areas got logged E and the column got added. And now you're trying to do a same scatter plot, the rig plot between log this column and the species column instead of the areas column and species column. So now when you're running it, now you can see that there is a stronger correlation because the points are more scattered around the line. So the estimated and the observed values are little clearer than this particular graph, right? So whenever you're trying to, as a data analyst, you are trying to make some assumption, sometimes it's always good to consult. So many times better to consult with the subject matter expert to get the right kind of relativity so that you can actually prove that by your data. So if you've understood this, type U in the chat box. Thank you so much, Rajan sir. Thank you, Shivakumar sir. Yes, thank you so much, ma'am. Now, this is what we have done. Now, I'm just going to do the model summary. If you want to do the same model summary with log area. Now, when you did the model summary with, just area, you got P 0.001. But when you do, because here the diagram says there's a stronger correlation. Now you can see here the log area, the it is still lesser than 0.5, and you are still the correlation is more and more stronger, right? So you still reject the null hypothesis, which says those are not correlated, right? So many times it is always better to consult with the subject matter expert is this point, right? So now first thing we have clarified. So let us see other violations. Yeah, so Ritesh, in the same session, sir also, so what Ritesh says is his question is, Jay sir also told that when points are accumulated at certain edge, log transform always works. So it could be log, sometimes it could be square, it could be under cube root, right? So it is always good to consult the subject matter expert. There could be some rule of thumbs, but the point here is we want to infer right and not always rightly go ahead and use it. So even Jay sir also explains that. Yeah, thank you so much, Ritesh. So these are called transformations. So now what we have done here is we have transformed the area into logarithmic, right? So this is called a log transformation. The transformation could be cube root transformation, square transformation, like we are looking at the, S is equal to ut plus half at square equation example, right? So these are called transformations. So we have done one log transformation here, and we're able to see that the 3 diagram also there is correlation between that. So another error we might make when we are inferring from linear regression is beware of outliers and influential points, right? So whenever you plot a point, there will be some outliers, right? So now what happens is if the outlier, whenever you're trying to make an average example, so I'm going to give you a smaller example. Let's say we are trying to take a score of a class. I'm just going to give it with a small example. Let's just say the scores are like this. Say one student got 10 and the rest of the students, okay, I'm just going to say student 1 and the rest of the students got let's say 92 or 94. Okay, so now when you try to do an average, right? Okay, so average of all of these. Now you can see that the average comes to what? 65. I'm just taking a small example, but we know by seeing the data, we are able to understand that none of the students are like it is way off. The average is way off the actual average, right? So why that is happening? Because there is one outlier, which if you plot the graph, it is away from the actual distribution. So outliers can many times give you sometimes, some student might be like a top student and other data might be like, medieval, intermediate kind of this thing, and your average might get shifted. Not just average, many calculations might get shifted. So you have to be aware of the outliers, right? So sometimes it is always good to reject, so you put the outliers aside while you're making the assumption, right? So because see, many times you can hear, except for 2 people, the average is roughly around 90. Except for 1 student, the average is around 90. So now when you put out the outlier or the influential point, you'll be able to get a better assessment, right? So I hope this particular point is clear. So beware about the outliers. If this point is clear, type C in the chat box. Thank you, Vinitha. Thank you, Anita. What other measures are shifted apart from average? If I'm not wrong, it doesn't affect median or mode. Yeah, it doesn't. So I'm just giving you an example based upon what kind of function. I really like the curiosity that you brought in. Now I also have to think what others get shifted. But average was an easy to explain concept. But when you're trying to make assumptions, you have to be clear about that, right? So maybe towards the end we can just think, idea. It's very easy. You can also contemplate on it and get the points. But always be sure that whenever you're making an assumption or any model you are building, outliers sometimes are better excluded, right? So it's like that. Like many times happens, like for example, there is a sports team, but out of the school sports team, out of that, one person is like a national player, Now he's definitely an outlier. So he will score and his speeds will be different and all those things. And, the average of the school group and the, the national people would be different. So that is how you can see that there will be some differences coming in. Yeah. So the next the next point that you have to be aware is correlation is not equal to causation, which is something like, for example, sometimes you can see that some areas, some things might be correlated, but it might not mean that they are causing something, right? So what this particular example says is like the sales of an ice cream from December to Jan had a graph which was similar to a graph which was of a forest fire, right? So the correlation, they might look, there is a relation, but it might not mean, it doesn't actually mean that their sales of ice cream caused anything, the fire or anything, right? So many times graphs might show you the correlation but not the actual causation, right? So this is what this point also explains, right? So sometimes two variables will appear correlated and there will be no obvious reason why, right? Sometimes two variables will appear correlated because an outside factor called a lurking variable is causing change in both, right? So this is something that you might want to. So as we can see above, the ice cream sales don't cause forest fires. However, both increase in summer months and decrease in winter months, right? So I hope this particular example was also clear. Right. So these are a few points that you have to, be aware when you are trying to make an inference from the summaries. Right. Now, let us look at another example. This is also an interesting example. So now, if you understood all the 5 points, all the points that we have discussed about, type U in the chat box. Okay. Thank you, Siva sir. Thank you, Ritesh. Thank you, Ravindra sir. So now in this example, so what they have done, this was, I found this interesting. Now what they did is they were, this particular data set compares sleep, right? And in that sleep, they have given the definition of all the columns that they have in that particular data set. So first I'm going to run the data set. First I'm going to import this data set into sleep. And you can see that these are the columns: animal, body, brain. Let us try to understand. So the variable animal tells the name of the animal. So let's say there's baboon and there is a rat and all those animals are there. And what is their body weight? What is their brain weight? And their slow wave, SW sleep means the number of hours of non-dreaming sleep. So when you sleep, there is a portion of time which is non-dreaming sleep and there's a portion of time where is a dreaming sleep, right? So which is also related to your eyeball movement, right? So here, interestingly, what they're trying to see if there is a correlation between the non-dreaming sleep or the slow wave sleep and the para sleep, the dreaming sleep. So this is what they are trying to do. The total sleep, the life expectancy of that particular animal, the gestation period of that particular animal. There's something called predation index. Here what they tell is if it is 1 and 5, so basically 5 means that most likely to be preyed on, least likely to be preyed on, meaning here in this particular example, if for example lion is there, it is on the hierarchy, highest hierarchy of the in the food chain, and it is less likely to be preyed on, right? So that is what is being given. So that is not relevant for our example, because we are only going to compare SW sleep and para sleep, right? So this is the data set. Now what we are trying to do here is first going to plot our scatter plot and see how it is looking. Okay, now we can see that there is some relationship between non-dreaming. So now we are just going to go ahead and see what the model also says, right? So the null hypothesis would be that there is no unrelated, like both of these are not related. The alternative hypothesis is that they are related and the slope is non-zero, right? So this is what we are coming, right? So the null hypothesis and alternative hypothesis are formed. Now let us try to do the model. Now we can see that the p-value is 0, which means the null hypothesis that they are not correlated because this is less than 0.05 is to be rejected, and we know that there is some correlation in that, right? So the para-sleep and sleep are being modeled here. Now the diagram also says that there is some correlation. Okay, so we have understood this. This is just an example of the same points, right? So we are redoing the same things. So now we reject the null hypothesis and conclude that there is statistically significant relationship between the amount of non-dreaming and dreaming sleep a mammal gets daily. So what other factors might be related to how much dreaming sleep a mammal gets? Let's look at life expectancy. So they are like right now comparing the para-sleep with life. So now we have compared sleep with para-sleep, the non-dreaming and dreaming phase. We understood that is correlation, right? So that is clear. Now we are going to compare with life expectancy and para-sleep. Okay, so now you can see that the data is more towards one edge, and here what we are directly going to do is do the model summary of the same, right? So here the life expectancy is 0.08, which is greater than so the p-value is greater than 0.05, meaning that we reject the null hypothesis. The null hypothesis was para-sleep and life are not related, and now we fail. Yeah. Yes, Ritesh, the value p-value would be same. Even if you look at the t-test also, the p-value will be same, right? Yeah. So the p is greater than is probability that the null hypothesis is true, right? So now what we are doing here is now p is greater than 0.05, right? Here we accept the null that they are not related, right? So now this is very clear. So now I hope it has become clear on how to read the diagrams and how to read the model summaries also. This also strengthens our previous understanding of t-test concepts because we are in a way revising that as well, right? So if it is clear till now, type C in the chat box. Thank you, Ritesh. Thanks, Prashant. So people who are watching us on our social channels, you can use the chat section. Thank you, Ravindra. Yeah, so now basically, there are a few other rules of thumbs that are being mentioned here. So we are going to try comparing not just one, we're going to also compare others, right? So other columns. So now one thing is anytime you see a relationship that looks like a flattening curve, right? Where if you look at any logarithmic curve, so the log curves are always, they start with a high drop or high gain, they become flat. So whenever you see the diagrams like this, so I'm just going to show you here. So whenever you are trying to see it is kind of flattening like this, you can maybe understand maybe this could be a logarithmic relationship, though we'll always consult with a subject matter expert, some rule of thumb, right? So if the graph looks like this, you can see that maybe the relation could be exponential, and here it looks more linear, right? So S and T are directly related. Here S and log T are related. Here S and T square or the other exponential is related. So this is how linear, no slope. If there is no relation, then this is how it would be. So this gives you a rough idea, but even Jay sir says like this is not something that you can work as a rule of thumb, but gives you a little understanding. Could be logarithmic or could be exponential like that, right? So now what we are going to do is also logarithmic we have understood. When it is a flattening curve, probably it is a logarithmic because logarithmic are easy to understand, right? So they start with a high rise or high drop and then go flat. So now what we are going to do here is we are going to do a dist plot on parasleep. So this is just for assumption when you are trying to do your exploratory data analysis. People who have joined recently, all of this is covered in our exploratory data analysis modules, which is here. So we have covered them from here, make features and exploratory data analysis. So do not worry, if you cover that, you'll be able to understand all of these, right? Similarly, the log life. So if at all we want to compare the log life with the parasleep, we can always go ahead and do that, right? So earlier we compared with life, now we are comparing it with log life. Now here we could see that parasleep and life did not seem heavily related, but parasleep and log life seem to be a little related, right? So now how is the model fit now for with parasleep and log life? So we are going to check that. Now you can see that here the p-value is less than, is it less than? Yeah, it is less than 0.05, right? So where we reject the Ritesh asks, log transform also helps to remove the skewness in a distribution. I think I'm not exactly sure on this, Ritesh. Maybe I'll come back on the upcoming session, right? So what your question is basically, when I think log transforms helps us do a lot of things, especially in the graphs. But if at all you are reiterating the same point, where the skewness, the slope of any distribution is being removed by using, okay. So I think Ritesh, it could probably true, because on the face of it, it looks the skewness could be removed, but I want to back it with some evidence. So I'll come back on this in my upcoming session. So let me make a note of that. Okay. So yeah, so we are trying to do different kinds of experiments here instead of directly comparing life with parasleep. We are trying to compare it with log life. So why are we doing all this is whenever now we are doing it in one over one, but we'll also be seeing how to compare all of these. Are there models to compare all of this and give us, I think this is a logarithmic or a quadratic relationship. So there are some ways to know the relationship, but here we are kind of doing the trial and error method, right? So we are trying to see if the parasleep is related to log life, right? So you can still say that what is the conclusion here? The p-value is still less than 0.05. So which means, is it less than 0.05 or 0.05? So we reject null. Great. So which is still in alignment to our comparison of parasleep with log life. So we still rejected the null there as well, right? So we did that, right? So now it's always good to work with a subject matter expert in these conditions, but whenever you are trying to do the assessment, you can always go ahead and do a little experimentation, right? So this is what we have done. And like we did in our previous 3.1, so how we started our session, similarly here also you can go ahead and do the prediction and the calculation of the residual, right? So this is also done here for us, right? So there's nothing specific we are trying to do here. It's more of an experimentation here. So what James explains here is a little experimentation he did, and he could see that there is a relationship between brain and body, which was not directly straightforward. The parasleep and the brain, or the parasleep and body, was not related, but he could do something called brain ratio, right? So here it was not logarithmic, it was a ratio. So let me go ahead and explain that. So now what we're going to plot the brain and parasleep. When we are plotting brain and parasleep, you can see that they seem not related, and they are not. Then what we are going to do here is we're going to do p-value or the r-value here. So we can see that the correlation coefficient is 0.95, right, which is a strong correlation, right? Our brain and body side correlated, right? So we've understood it, yeah. So now how are they correlated? Calculate. Now what he has done here is he added a column which is brain ratio, which was the brain weight divided by body weight, and then he tried comparing both of them, right? So then a scatter plot was done. You could see that it was a little better related here, right? So this is a little experimentation that we do, but now you can understand that how to try to generate or see if there's a relation or not, right? So now when you do the parasleep and the brain ratio, the p-value is 0.81, which is higher than our 0.05 significance, and that for that reason we accept the null hypothesis, which is they are not related, right? So this is a little bit more of learning, experimentation and all. So as we proceed forward, we'll have clearer and clearer models for the same, right? So I hope the OLS regression was clear, and also how to infer from that is clear. If this portion of that is clear, type C in the chat box. Thank you, Ritesh. Thank you, Anita. Thank you, Ravindra sir. Right. So, as I've explained, a few, rule of thumb graphs were given here, but, there's nothing specific that you can always use it. Right. So this concludes our session. And in our upcoming session, we're going to cover the next model, the next module, which would be the multiple linear regression. This will happen on our Wednesday, right? So we'll do it on Wednesday, but I'd request you to go through the assignment portions, the people who have finished or following it, in the sequence. People who have not, who have recently joined, I'd request you to go through the lectures from the beginning and bring us any questions if you have in our upcoming session, right? So I would request if there's any other question apart from this particular lecture, you can go ahead and put it on chat, or unmute and ask me, or anybody else might also be able to help. Apart from the access related issues, access related promotes, I'll take some time and help you out here. Okay, so I hope everything is clear, right? So for a final assessment, if you have found this session clear, type C in the chat box. Great. Okay. Thanks, everyone. So I see that there are fewer queries or no queries today, but I would request you to bring in more for our upcoming session. So people who are interested in continuing the momentum, thank you, Tejinder sir. Thank you, Sivakumar sir. Thank you, Radha sir. It was explained very clearly. Thank you so much, Ritesh. Right. So if you want to keep up the momentum, you can go ahead and finish the 3.3 before our Wednesday session, so that it will be actual revision as well. Great. So thanks everyone for joining in. I hope you have a very good weekend ahead. Thank you so much. Thank you, Ritesh.